Imagine waking up one morning to find your phone disconnected, GPS signals unreliable, and even the power grid struggling to keep up. Sounds like a science fiction scenario? Well, this could be the reality in the face of an intense solar event. On July 23, 2024, a massive solar flare was observed on the far side of the Sun. Thankfully not aimed at Earth, but with enough power to remind us of the Sun's hidden threats. Solar flares and coronal mass ejections, CMEs, aren't just distant, abstract phenomena. These bursts of solar energy can unleash storms of radiation, disrupt communications, and even cause widespread blackouts if they directly strike our planet. As our society grows increasingly dependent on technology, understanding the risks of solar events and our readiness to protect against them has become crucial. Let's explore how these invisible forces from space can impact our daily lives and what scientists are doing to keep us prepared for a possible cosmic catastrophe. Curious about how the Sun's activity can impact life on Earth? Hit that subscribe button to stay informed. Observation of a solar flare in July 2024. On July 23, 2024, the Solar Orbiter spacecraft, a collaborative project led by the European Space Agency, observed a powerful solar flare on the far side of the Sun. This observation was critical not only for understanding solar behavior, but also for assessing the potential threats such events pose to Earth. Though not the most intense flare ever recorded, scientists noted that it was classified as an X14, one of the stronger types. Had this explosion of solar energy been aimed directly at Earth, it would likely have triggered severe consequences, from electrical blackouts to disruptions in communication systems worldwide. A reminder of the Sun's hidden power and the risks associated with such events. Solar flares occur frequently during the solar maximum, the peak phase of the Sun's 11-year cycle when solar activity intensifies. During this period, the Sun's magnetic field is particularly active, leading to frequent crossings, shifts, and reconnections that result in the release of energy as solar flares or coronal mass ejections, CMEs. These energetic bursts, like the one observed in July, propel streams of particles and radiation into space. While most solar activity goes unnoticed by people on Earth, scientists carefully monitor it because of the serious effects it can have on technology and infrastructure. The recent event highlighted the need for ongoing space weather monitoring. Solar Orbiter's observation allowed researchers to study a solar flare occurring on the Sun's far side, far beyond Earth's direct view. Data from such events help scientists predict the strength, behavior, and potential impacts of future solar flares directed toward Earth. This type of research is crucial for developing timely protective measures to shield satellites, power grids, and other critical systems from catastrophic failures during extreme solar events. Had this solar flare's intense radiation been directed toward Earth, the consequences could have been severe. A direct impact from an X14-class solar flare has the potential to disrupt radio communications, satellite operations, and even some portions of the global power grid. By closely examining these events, scientists hope to better predict when and where solar activity may threaten the Earth, allowing for advanced preparations that mitigate the risks associated with solar flares and CMEs. What are solar flares? Solar flares are powerful bursts of radiation that occur when magnetic fields on the Sun's surface become extremely stressed and unstable. These magnetic fields, generated by complex movements within the Sun, continuously twist and bend, especially during periods of high solar activity, such as the solar maximum. When the magnetic fields intersect or reconnect, they release tremendous amounts of energy in the form of light, X-rays, and other forms of radiation. This process accelerates charged particles, producing intense solar radiation that travels across the solar system at nearly the speed of light. The intensity of solar flares is classified into categories, ranging from Class A, the weakest, to Class X, the most powerful. Within these categories, the number following the letter further specifies its strength, with higher numbers indicating more powerful flares. For example, an X14 flare, such as the one observed on July 23, 2024, is considered extremely strong and capable of causing significant disruptions on Earth. These classifications are crucial for determining potential impacts on Earth's technologies and preparing for necessary protective measures. During solar maximums, the frequency and intensity of solar flares increase, bringing an elevated risk of space weather events that can affect Earth. Space agencies and scientists monitor these cycles closely to predict the likelihood of extreme events. Unlike smaller solar flares, which might not reach Earth or cause noticeable effects, larger flares have far-reaching consequences. For instance, the radiation from strong solar flares can interfere with GPS systems, radio communication, and satellite operations, which are essential to daily life and global infrastructure. Beyond their immediate impacts, solar flares also contribute to other forms of solar activity, including coronal mass ejections, CMEs. CMEs are large expulsions of plasma and magnetic field from the sun's outer atmosphere, or corona, which are often associated with strong flares. When these CMEs interact with Earth's magnetic field, they can trigger geomagnetic storms and auroras, illuminating the night sky with vibrant colors. Understanding the mechanisms behind solar flares and their connection to CMEs is essential for predicting and preparing for these phenomena. Consequences of solar flares and CMEs. Solar flares and coronal mass ejections, CMEs, can have significant consequences on Earth, particularly in terms of disrupting human technology and infrastructure. CMEs, in particular, are explosive ejections of solar matter that travel at speeds exceeding 1.5 million kilometers per hour. When these charged particles collide with Earth's magnetic field, they can disturb the planet's geomagnetic stability, causing effects such as auroras, radio blackouts, and damage to satellites. A direct hit from a high-intensity CME or solar flare could trigger geomagnetic storms with wide-ranging impacts on our daily lives. One of the most immediate threats from solar flares and CMEs is their impact on satellite operations. Satellites play a crucial role in global communications, navigation, and weather forecasting. During intense solar activity, the atmosphere expands due to heating, increasing drag on satellites in low Earth orbit and causing them to descend, as happened in the Starlink incident of 2022. The heightened drag and radiation exposure can compromise satellite functionality, shorten their lifespan, or even cause them to burn up upon re-entry. The power grid is another critical infrastructure at risk during extreme solar events. Geomagnetic storms can induce currents in power lines, leading to power surges that may overload transformers and disrupt electrical systems. For instance, the 1989 geomagnetic storm in Quebec, Canada, caused a massive blackout, affecting millions of residents. In a world that relies heavily on electricity, such power outages can bring entire regions to a standstill, affecting industries, transportation, and even emergency services. Thus, the effects of solar flares and CMEs extend far beyond the scientific realm, posing real challenges to modern society. While the immediate effects of solar flares and CMEs are concerning, their long-term impacts on human technology and infrastructure cannot be ignored. As we continue to expand our reliance on satellites and interconnected electrical systems, the risk of widespread disruption from solar events grows. Scientists and policymakers are working together to create stronger protective measures and develop early warning systems, which could give us valuable time to protect our assets from potential solar catastrophes. If you're finding this information valuable, give us a like and let us know what surprised you the most about solar flares in the comments. 4. Historical solar flare events and their impacts. Throughout history, several solar flare events have left lasting impacts on human society, highlighting the potentially devastating consequences of extreme solar activity. One of the earliest and most notable events was the Carrington event of 1859. This powerful solar storm produced auroras visible as far south as the Caribbean and disrupted telegraph systems across North America and Europe. In some cases, telegraph lines reportedly sparked, and operators experienced electric shocks due to the induced currents. This event, although occurring before the age of modern electronics, underscored the power of solar storms to disrupt human technology. Another significant solar event took place in March 1989, when a geomagnetic storm caused by a CME led to a major blackout in Quebec, Canada. The storm overwhelmed the region's power grid, leaving approximately 6 million people without electricity for 9 hours. This event demonstrated the vulnerability of modern electrical infrastructure to geomagnetic disturbances and raised awareness about the importance of geomagnetic storm preparedness. Since then, power companies have worked to reinforce grids to withstand similar solar storms, but the risk of widespread outages remains. More recently, solar storms have continued to impact satellite technology and other critical infrastructure. In February 2022, 38 Starlink satellites launched by SpaceX were lost due to a geomagnetic storm that increased atmospheric drag, causing the satellites to re-enter Earth's atmosphere and burn up. This event highlighted the challenges faced by space-based infrastructure and the potential for economic loss when solar activity intensifies. As satellite technology continues to advance, protecting these assets from solar activity has become a priority for both public and private entities. These historical events serve as reminders of the need for proactive measures to guard against the impacts of solar flares and CMEs. As solar observation technology advances, researchers are hopeful that future solar storms can be predicted and managed more effectively. While we cannot prevent solar storms, improved forecasting and infrastructure resilience may allow us to minimize their disruptive effects on society. 5. Impact on satellites and modern infrastructure. Solar flares and geomagnetic storms pose a direct threat to satellites, which are vital for telecommunications, GPS navigation, weather monitoring, and scientific research. When the sun releases a powerful flare or CME, the burst of radiation and charged particles can interfere with satellite electronics, cause power failures, and even physically damage components. In cases of extreme solar activity, satellites in low Earth orbit face increased atmospheric drag, which can pull them out of orbit and lead to their destruction, as seen with the Starlink satellites in 2022. Apart from satellites, geomagnetic storms induced by solar activity can have severe consequences for power grids on Earth. These storms create electric currents in power lines and transformers, which can lead to overloads and equipment failures. In vulnerable regions, such as high-latitude areas, these geomagnetically induced currents can cause large-scale blackouts. The Quebec blackout of 1989 is a prime example, as it left millions without power and showcased the cascading effects that a solar storm can have on interconnected electrical systems. Solar flares and CMEs can also affect air travel, particularly in polar regions where pilots rely heavily on GPS and communication systems. During periods of intense solar activity, airlines may reroute flights to avoid the highest levels of radiation and ensure reliable communications. This is not only a logistical challenge, but also incurs additional fuel costs and delays, impacting the airline industry financially. For these reasons, space weather forecasting has become an essential tool for airlines and other industries dependent on satellite technology. To address these risks, scientists and engineers are developing stronger protective measures for satellites and other critical infrastructure. Enhanced shielding, reinforced power grids, and improved early warning systems are some of the steps being taken to safeguard technology from the unpredictable nature of solar storms. While the threat of solar flares and CMEs cannot be eliminated, these advancements aim to reduce the likelihood of widespread outages and damage, preserving the technological systems that modern society relies upon daily. The future of space weather prediction. Advancements in space weather prediction technology are crucial in preparing for future solar events. Scientists are continuously developing tools and models to improve our understanding of solar flares, CMEs, and their potential impacts. With spacecraft like the Solar Orbiter, which captured the July 2024 flare, and upcoming missions focused on space weather, our ability to monitor solar activity is steadily improving. Real-time monitoring allows scientists to identify emerging patterns, giving earlier and more accurate warnings of geomagnetic storms. One promising area of research is the development of predictive models using artificial intelligence, AI, and machine learning. These technologies can analyze vast amounts of solar data to forecast when and where solar flares and CMEs are likely to occur. AI-driven models are becoming increasingly sophisticated, capable of identifying the complex interactions within the sun's magnetic fields that precede solar events. By better predicting the timing and intensity of these events, scientists can help minimize their impact on Earth's infrastructure. International collaboration also plays a vital role in space weather prediction. Since solar events affect the entire planet, organizations like the European Space Agency (ESA), NASA, and the National Oceanic and Atmospheric Administration (NOAA) share data and expertise to improve global preparedness. The hope is that with coordinated monitoring and forecasting efforts, governments and industries can take preemptive actions to protect critical assets and services, reducing the potential damage of future solar storms. As we've seen, solar flares and geomagnetic storms aren't just topics for scientists. They're forces that could upend our way of life. From impacting satellites to straining the power grid, these cosmic events demand our attention and preparedness. Are we ready for a world where a single burst from the sun could disrupt technology and society? What steps are we taking to secure our digital and physical infrastructure against these powerful solar phenomena? Preparing for the next big solar event isn't a question of if, but when. So, stay informed, keep questioning, and take an active role in learning about space weather and its potential effects. Don't forget to subscribe and turn on notifications so you can stay up to date with new insights on protecting ourselves from the next solar threat.